Rightio, this video is about rate of reaction. Some people freak out on rate of reaction, that this means the speed of the reaction, and it's all about how fast reactions go, how you can speed up or slow down a reaction, and how to actually keep a track of how quickly the reaction is going, what's the speed of it, and that's what we're going to look at first here. We're going to look at, just use the reaction between marble chips, chemical name calcium carbonate, an ionic compound, calcium ions, carbonate ions, and hydrochloric acid, HCl. And first off, we're going to look at keeping a track of the rate of reaction, and especially how it changes and how we can show that. So I've got in here some marble chips. I've got some hydrochloric acid in this beaker. It's sitting on an electronic balance, so the mass is shown there. At the moment, just the chips in the beaker have a mass of 71.39. Now, being a carbonate and an acid, we know that we're going to get water, we're going to get a salt, in this case calcium chloride, we're going to get a solution of calcium chloride, and we're also going to get gas. The gas is going to leave the beaker. The gas is carbon dioxide. The carbon dioxide is made from the carbonate ions, which are currently in the marble. So mass is going to break down, the molecule is going to break down and leave the beaker. So the mass should fall. So there we go. I've poured the acid in, so it's gone up for the moment. But as the gas leaves the beaker, you should see the mass has fallen there. It's gone from about 90.44 and it's rapidly gone down to 90.25, 0.24, dropping below 0.2. It's now 90.1614, dropping rapidly as the mass is leaving the beaker. And that's one way you can keep a track of the rate of the reaction. What you could do is, if you could be quick enough, you could look at the time in seconds here, and you would say after 1, 2, 3, 4, 5, 6, 7, 8, 9 seconds, for instance, what has happened to the mass. Eventually you'll find that the amount that the mass goes down by starts to get smaller as the reaction slows up. The reaction eventually is going to stop, so in between times it's actually going to start slowing down. So I'm randomly making up 10 data here. But if we were to put this data on a graph, we would put the mass in grams on the side axis, and we just have the time in seconds or minutes or whatever unit we're using, depending on how quick our reaction is. And our graph would show that the mass was quite high to start with and it dropped. And so if we plot these on the graph, eventually one or other of the reactants will be used up here. The marble chips will be all dissolved away, which looks like it is the case here. The marble chips have gone, so there must be some leftover hydrochloric acid. So our graph line looks like that. So right now, after, I don't know, 60 seconds, our reaction has stopped. And in our case, marble chips have run out. CO3 is all gone. And that is the reason the reaction has stopped. So the reaction rate there is 0. And there is no slope on that line, and it is the slope of the line, just like in the mechanics, the slope of your line tells you how much acceleration or how much speed you've got. It's the same here. The steeper the line, the faster the rate. The fastest rate is at the start. Okay? Line is the steepest. Now this is all lots of A marks on this. Fastest rate, line is steepest. And getting into the reasons for that, the factors, which are always temperature, surface area, concentration, you're starting to get into merit marks. Why is it fastest there? You say it's got the HCl concentration is biggest, highest, And also we have quite a few little marble chips in there. The surface area was highest. Okay. Now, as you notice immediately, the line begins to get less steep until it flattens out. So down here, we have the other end of the scale where the concentration of HCl is lowest, and surface area. In our case, the marble chips have actually gone. There is no surface area. Surface area at its lowest. So if you have a solid, you can mention surface area. If you just have liquids, you could only mention concentration or temperature. We're assuming the temperatures stay at room temperature. So here in the middle, the reaction is slowing down, the rate is slowing down. Concentration getting less, and surface area getting less. Okay, now that sort of covers achievement and merit marks. There's usually 1 or 2 achievement marks, certainly possibly 1 or 2 merit marks there. The excellence comes into talking about the particles and what the particles are doing as those things change. So I'm not doing excellence here. Here is another method of tracking the rate of reaction. Again, I've put in a little paper package of marble chips to try and keep them together and keep them under the cylinder there. And I'm going to tip in some hydrochloric acid from this beaker. And in this case, this cylinder here is full of water. And I could make a reading every 5 seconds of how much carbon dioxide is building up in here. So it's going to bubble away down there. The bubble's going to float straight up. And this is going to fill with gas instead of water. And the water is going to drop out as the reaction goes on. Okay, so I'm going to add that, and to get our graph, I would every 5 seconds maybe I would take a reading, or get someone to shout out the reading on the cylinder of the volume in mils. So our graph this time, which I'm going to put over here, is going to be a graph of volume of gas. In this case, CO2, and that's going to be in mils, versus time. You know, if I was doing this for real, I'd probably just go every 5 seconds, I think. So that would be time in seconds or minutes, depending on how fast the reaction is. I'm expecting this is going to be a reasonably fast reaction. It takes a while for the acid to mix through and start reacting, and the chips are wrapped in paper to keep them together. Hopefully they'll stay underneath the cylinder where we can start to catch the gas. So it's going to take a while for that acid to get into those chips and the gas to start forming. I hope I haven't put too much paper on there. I'll give it a little mix. You can see now that those bubbles of carbon dioxide are starting to go up there. The flow of hydrochloric acid into the surface area is going to be a bit low because the paper's in the way, stopping those little currents from circulating. But you can start to see now that I could make a reading off that measuring cylinder when someone calls out 5 or read or something like that. So in that case, because we started with a 0 volume, we would start with 0 mils of gas down here on the scale, and our graph would go something like that. Again, eventually the reaction is going to stop. The acid is going to be used up, or marble chip is going to be completely used up. But again, it is the slope of the line. It's exactly like that. The slope of the line tells you the speed. A steep slope shows you the fastest reaction. Okay, so that is the fastest rate, and that is because it's got the steepest line. Okay, again, rate is slowing as the concentration and the surface area getting smaller causes the rate to slow down, and up here, of course, it is stopped because the slope of the line is is 0, and either the Ca to CO3 or HCl is used up. Okay. So we've already constantly mentioned three factors that, or two factors that change the rate of the reaction. Okay, the concentration and the surface area change the rate of the reaction. The third one you're expected to know about is temperature, and all three of them, if you increase them, they increase the rate of reaction. If you increase the surface area, increase the concentration, increase the temperature, the reaction speeds up. And quite logically, amazingly for science, if you reverse those things, then the rate will drop. I'll just move that a little bit so you can see this axis with the volume of CO2. That's the volume of CO2 in there.